Math 230, Cuesta College. I'm Joe Vasta, and today we are covering section 5.1, graph theory. So you may have remembered these little puzzles from when you were a kid, or maybe not. But it goes, can all the edges be traced with a pencil only once without lifting the pencil off the paper? So, here's just a bit of scratch paper here. I'm going to try this middle one here. And so, let's see. Okay, so only one. So I got stuck right there. I can't do this problem. It doesn't seem like I can do it, but it doesn't mean it's not doable. So you can only go over an edge once. You can't lift the pen off the paper. See, when I was stuck here, I did not do that edge there and then the edge that connects there. But I can't get over there because I've already done those three edges. So maybe you want to pause the video and see if you can do these three problems. I mean, the answer might be no. Okay, so let's go ahead and see if we can do them. Now, if this were a face-to-face class, this would be like one of the few times I'd have people go up to the board and, see if they can figure these out. So what I'm going to do is I'm going to go to the middle one, the one I failed on, and I'm actually going to, here's the piece of paper, I'm going to try to do this again. And this time I'm going to start right down here at this corner. So I'm going to go like this. And I did it. Okay, so problem number 2. The answer is yes. We can do this. The answer is yes. For problem 2. I'll just put the answer like way above. And if you wanted to see what I did, I think I did this. And this is just to kind of show you what I did. I think I went around the whole outline of this house here. Then I went up like this, that, and down. So that's what I did. So that answer is yes, we were able to do it. Let's go ahead and do another problem here. How about problem number 3? If we do problem number 3, maybe I'll start in the middle here. So I'll go down this way, then I'll go down, up, around. Yes, so I did it. So what did I do? I'll go ahead and trace it out here so you can see. I think I went around this triangle first, so hopefully I can do the same thing. And then I don't think I went down there. I think I went up. In any case, that is the path that I took. Okay, now you may have been able to do these problems and maybe you started in different places, but the fact is that this problem seems to be one that you cannot do. And so these are the problems you're going to be getting in your homework, and you want a better way of doing these 3 problems than just saying, let's see if we can draw this like 17 times. So let's take a look at what I've done here. The answer to this one is yes. And the answer to this one, I'm going to tell you right now, it is no. But we have to actually have a good method, so we're 100% positive to write no there. So let's go to the middle problem, and let's make this clarification that I started at this point here. Okay, so now we want to have a name for those points. Let's get into graph theory. So a graph, that's what these three things are. Those are graphs. They are made up of vertices. The singular is vertex. They're made up of vertices, those are the dots, and edges. And those are the lines. So that's what a graph is made up of, vertices and edges. And when we ask this question, can all the edges be traced with a pencil only once without lifting the pencil off the paper? That's a property. And when we ask about that property, it has a name. And that name is traversable. So instead of saying this graph has the property that all the edges can be traced with a pencil only once without lifting the pencil off the paper, instead of saying that, we can say that this graph right here is traversable. Graph number 3 is also traversable. And graph number 1, even though we didn't show you yet, this is going to be not traversable. Okay, so I want to get back to graph number 2, and the reason I went ahead and did this is because I want to start at this vertex. Okay, start at this vertex. I want to ask you, where did I end when I did this little journey? Let's call it a journey. Well, I ended right here. And notice, think of this as 6 cities, and you're taking a travel, and you're visiting these 6 cities, and sometimes you're traveling, like for this city, you visited it twice. You know, when you started, you came here, and then you came into the city, but then you left this city. Okay, we're talking about this one right here, so let's have an arrow pointing right there. But then you came back into the city again, and then you left the city. So this city here, if you look at how many edges are coming out of it, there are 4 edges coming out of that city, out of that dot. And that kind of makes sense because on your journey, you had to enter that city 2 times, and you had to leave that city 2 times because it wasn't your starting point, it wasn't your end point. Let's take a look at this city up here. Well, when I went on my journey, I came into that city 1 time, and I left that city 1 time, which means if you're looking at that city, how many edges are coming out of that city? Well, 1, 2. So I'm going to put a 2 here. All the other vertices or cities where you did not start or end should have an even number, because the even number kind of denotes that you came into that city the same number of times that you left that city. So if we're looking at this city or vertex, I've been calling them cities, I have how many edges going out of that vertex? 1, 2, 3, 4. So this makes sense. I hope it makes sense. This middle city, I mean, you can look at this journey. I entered it twice and I left it twice. But if you look at this, you count the edges coming out. 1, 2, 3, 4. Now, let's look at the place where you started. Look at the number of edges coming out. 1, 2, 3. So there are 3 edges coming out. And that's different. That's not an even number, is it? Now, why is this an odd number? Because on this journey, you left this city 2 times. When you first left it, and then when you came back to it, you left it again. So these are the 2 lines, these are the 2 edges where you left the city. You left the city 2 times, but you came back to it 1 time, which gives you an odd number. Now let's look at our end point, which is this one right here. How many edges are coming out of that vertex? Well, 1, 2, 3. So I'm going to label that 3. Now this one's an odd number because you arrived in this city, you arrived there 2 times, and you only left it 1 time. And the reason why you arrived 2 times is because the last thing you did is you arrived to that city. So that's why the end point is an odd number. The start point is an odd number, which makes this traversable. You know a graph is traversable if it has 2 odd vertices. 2 odd vertices makes the graph traversable. Now let's move over here. This graph right here, let's label the vertices. You might want to pause the video and see if you can label each of these vertices. And that labeling them means putting a number next to each of them, and that number denotes how many edges are coming out of it. So see if you can do that. Okay, so this vertex here gets a 2. 1, 2. This vertex also gets a 2. It's almost as if this diagram is the same as that diagram, except it has an edge missing. So you're going to see some similarities with the other ones. Look at this vertex gets a 4. This vertex gets a 4. The one here gets a 4. And the one up there gets a 2. So this graph has vertices that are all even, which is different from this one, but we had yeses on both of them. So could you think of why this one has 0 odd vertices? And I'm just going to tell you, because look at your journey here. You start and end at the same vertex. So because this one had all even vertices, I could have started anywhere. Let's see if you can see if I'm cheating on this. I'm going to start at the top. I'm not going to write on this. I'm going to tell you what I'm going to do. I'm going to go down there, over to the middle, up there, across, down, there, up, and then back to my starting point. So you can start at any vertex as long as you're careful, and maybe going slow will help you be careful. You can actually draw the diagram. You didn't have to start in the middle. But on this one, when you label a graph and you have 2 odd vertices, you must start at one of the odds and carefully go, and your end point will be at the other odd. So I could have started there on the bottom right vertex. If I was careful, I would have ended at the bottom left vertex. So that's how you do these things. Your graph is traversable. That means it has this property, which I don't have to keep saying. If your graph has 2 odd vertices or 0 odd vertices. So let's go ahead and take a look at problem number 1. This vertex here gets a 3. 3. The middle one gets a 4. Up here, 3. And then up on the top left, 3. So guess what? This one has 4 odd vertices. So the answer is no. Now, the thing that I did not do with you guys before we move on is the puzzle. What do these letters have in common? So here's some letters of the alphabet, and you have to tell me what they have in common. How come we don't see the letter B or the letter C in this list? And at the very end of this lecture, we'll give you the answer. Okay, so we need to look at a definition. So I'm going to write out the definition here. I didn't have it written out in advance. Oh well. A graph is traversable if and only if the graph has 2 or 0 odd vertices. Okay? And so we have yes when we had 0 odd vertices and yes when we had 2 odd vertices. But if you have another number of odd vertices like 4, the answer is no. Okay, now we're going to do another definition here. So for some reason, maybe when you're doing circuits or things with wires, it is desirable to have graphs that look like this, because graphs that look like problem number 3, starting and ending at the same place, is something that's very desired sometimes. So we have a special name for that. And now we'll put it right here. So we can say this is a definition of traversable. A graph with no odd vertex is called, and I'm just going to write it down here. So what does that word look like? It looks like Euler, but it's not. It's Euler, so it's pronounced Euler. So that's called an Euler circuit, a graph with no odd vertex, or you can say 0 odd vertices. So let's take a look at our problems here. So the one that has no odd vertex would be problem number 3. That's called an Euler circuit. Okay, so this has 2 odd vertices. It may have been traversable, but this one's not an Euler circuit. And this graph right here has 4 odd vertices. It's also not an Euler circuit. Okay, so let's mention a few things before we get to the next question. Few things we want to say. I'm going to make this be a definition like in a different color, maybe blue. It's not really a definition, I'm sorry, it's a theorem. Because some of you might have been thinking about this. Notice, before I write this theorem down, our graphs, we had 0 odd vertices, 2 odd vertices, 4 odd vertices. Can we ever have a graph that has an even number? Can we ever have a graph that has an odd number of odd vertices? So I said that wrong. So could we ever have a graph that has like 5 odd vertices? And the answer is no. So this is a graph theory theorem, and I've thrown it out here, not that you have to memorize this, but it says this: every graph has an even number of odd vertices. Okay, and so that's a graph theory theorem. We're not going to start proving these theorems, but if you'd like, you can try to come up with a graph. Try to break this theorem. Try to come up with a graph that has an odd number of odd vertices. You'll never be able to do it. Okay, so there we have it. The other thing that I want to point out with traversable and Euler circuits is I'm going to make a connection to our first topics, some of the first topics we were doing. One had to do with Venn diagrams. So I'm going to let my universal set be graphs, and some of those graphs are traversable. So I'm going to make a circle. I'm going to say traversable. I'll shorten it. And notice, all Euler's circuits are traversable because traversable graphs allow for 0 odd vertices, and this is 0 odd vertices. So I'm going to put a circle in here. I'm going to say this is an Euler circuit. So for our problems, we have this Venn diagram here. This guy right here, problem number 1, was not an Euler circuit and not traversable. It belongs out here. There's number 1. Problem number 2 was traversable but not an Euler circuit. That belongs right there. That's where that graph lives. And problem number 3 was an Euler circuit and it was also traversable. So graph number 3 lives there in the Venn diagram. So you'll never have a graph that is an Euler circuit that is not traversable. That does not make sense. It kind of goes against these definitions here. Your graphs, when they give them to you, will fall in one of these spots on this Venn diagram. So some of you might be overwhelmed thinking, wow, we've been doing a lot of stuff. I don't know if I'll be able to do the homework. Let's go ahead and do some problems. I know there was a lot of writing here, and let me just, because some of you are going to be looking at the PDF box, the important parts here. So, not traversable, 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 not an Euler circuit, not an Euler circuit, Euler circuit. So we'll do, I think, 5 more problems, and then we'll come back to the puzzle. Here's what you do in your homework. For each of the graphs below, you answer these questions. Determine whether the graph is traversable, and if it is, show how. Determine whether the graph is an Euler circuit, and if it is, show how. So I'm going to go, here's A, here's B. Now this show how, this is good to know how to do, but when the test comes, I'm just going to be asking you the first part. Okay, is the graph traversable? Is the graph an Euler circuit? I'm going to show how when we do some of these. You know, I think on the 7 and 8, I don't know. We'll see how complicated the graphs are. So what do we have to do with these graphs? Well, you might want to pause the video and see if you can determine whether the graph is traversable and whether the graph is an Euler circuit. You can reproduce these graphs. One thing we notice about these graphs is the edges. can be curvy. Okay, so that's the flower graph. Okay, so I'm going to start right here. This vertex gets 2. Okay, why? Because there are 2 edges coming out of it. Now, if you're like having a hard time doing these labelings, just circle the vertex and then see how many lines it hits. So look, 1, 2, 3, 4. That means there's 4 edges coming out of it. This one's a 2. Up here is a 4. 4. 4. And then we have 2 right there. 1, 2, 3, 4. And then 2. Okay, so what do we notice about the vertices? Well, we notice that what do we have? There are 0 odd vertices. What does that tell me? That tells me that the first question here, is the graph traversable? Yes, it is. So the graph is traversable. Is the graph an Euler circuit? Yes, it is. Okay, so there it is. So this is where problem number 4 lives. Problem number 4 lives inside there. It's an Euler circuit and it's traversable. Now, if I want to try to reproduce this graph, okay, I can start anywhere I want to start. So that's what I'm going to do. So how am I going to reproduce this graph? Let's start right here at this edge. And then I just have to be careful. My job of doing this is going to look a little sloppy because I want people who are looking at the PDF to know kind of what I'm doing here. So I'm actually not going to touch that vertex when I come up there. I'm going to the middle, so there's the middle. And then I think I'll go this way. You just have to be careful not to trap yourself. Go down to the bottom, go this way. I suppose I'll go up to the middle again and then back to my starting point. I'm going to come down there, go this way, and then back up. And there it is. I know it looks a little sloppy. It doesn't look exactly like this, but I found that if I draw the pictures like this, people can analyze my path that I took a little easier than just drawing it without drawing the arrow and connecting everything. Then you don't even see what I drew. So yeah, I could have started anywhere I wanted because it is an Euler circuit and I could have completed the path. Okay, so now let's go ahead and do problem number 5. We'll label the vertices. This one gets a 3, 3, 3. So already, game over. Let's go ahead and label them all. So there's a 3 there, and oh boy, 1, 2, 3, 4, 5, 6, 7, 8. 3, 3, 3, 3. There are 1, 2, 3, 4, 5, 6, 7, 8. 8 odd vertices. So what does that mean? Is it traversable? The answer is no. Is it an Euler circuit? The answer is no. So this is not traversable and not an Euler circuit. And so that completes problem number 5. So because the answer is notable, there's no way I can show you how to do it because it cannot be done. Now when we first did our questions, can all the edges be traced with a pencil only once without lifting the pencil off the paper? If we didn't know about labeling the vertices, we could be looking at this thing for like minutes or even hours trying to figure out if we can do this or if it was not possible. But now we can label these vertices and we know for sure that it cannot be done. Okay, now the flower. So yes, this also illustrates that you can have a vertex that just has one edge coming out of it. And so this one gets a 1. 1, 2, 3, 4, 5. 1, 2, 3, 4. 4. 4. 4. 4. And 1, 2, 3, 4. So, wow, I just smeared that one. Okay. So how many odd vertices do I have? So that's what we do to do all these problems. We count the odd vertices. There's only 2 of them. 2 odd vertices. That was black ink there. I didn't mean to do that. And 2 odd vertices. Well, is the graph traversable? The answer is yes, it is traversable. Is it an Euler circuit? No, it is not an Euler circuit. So there's the answer right there. In terms of our Venn diagram, number 5 goes here, and number 6 goes there. Because it is traversable, I can trace it, and I'm going to trace it. So this guy right here was number 4. Number 6 I'll put right here. So let's see if we can do it. I'm going to start at one of the odd vertices. I think I'll start down here. So like this. Now I'm up at the 5. I'm going to go ahead and make the circle. Now I'm going to be hitting each of those vertices that have 4s on them with my edge here. Now I'm not going to touch it because I'm going to kind of do it like that diagram, and then I'm going to go ahead and make each of the petals. So we have that one, that one. So I've just done that one there. That one. And I'm not touching on purpose because I want you to see what I've done if you're looking at this again. And then I end up right there. So here was the start, and then this was the end. Whereas on this one, start and end were the same place. I'm not going to label those. So that is one way of doing the problem. You could have started off at the 5 there and done all the activity and ended up right there at the bottom. So this is how you do these problems when you hit your homework. Let's go ahead and do 2 more of these. Okay. Is the graph traversable? Is the graph an Euler circuit? The way you do these problems is you label these vertices here. Okay, I put this graph on here because this graph has something kind of new that the other graphs don't have. And I think it's this right here. So you might pause the video and see if you can do these on your own. Okay, so what is meant by this? Some of you might count this as a 3 because you see this edge here, 1, 2, and then you count this as the same edge. Well, the deal is we don't count this as the same edge. If you do that technique that I told you where you circle the vertex and say how many edges does that circle hit, it hits edges 4 times. So I'm going to go ahead and put a 4 there. Even knowing that, well, that edge kind of hooks up to the same edge there, it's the same edge, we put a 4 there because we say how many things are coming out of that. I'm going to do the same thing right there. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. This one just has a 1, and this one is a 1. So the deal is, how many odd vertices do I have? I have 2 odd vertices. What does that make it? Traversable but not an Euler circuit. So on the Venn diagram, number 7 lives here. Would I be able to trace number 7? This will be the last one that I do because I don't know what this one's going to be, but if one of those happens to be yes, there's no way I want to retrace that one. So I think I'll do number 7 right here. Okay, so here is 7. I can start at one of those legs there, so I'll start right down here. And then I go up around this diamond, and as I go, I'll go ahead and do the circles. Up here, down here, back down there, and then finish there. So we started here, we ended there. Okay, let's go ahead and do problem number 8. This picture might look familiar. This is a Venn diagram for 4 sets. Let's label each of these vertices. This one gets, I'll do it in red because that's what I've been doing, 4. This guy right here gets a 2, 4. There's a lot of vertices here. 1, 2, 3, 4, 5, 6. We have 4 there, 4 there, 4 right there. I'm counting the edges coming out of each vertex. 4 there, 2, 1, 2, 3, 4, 2, 4, 4, 4 for that guy, 4, 2, 2, and then there's this guy 4. I hope I got them all. Looks like a bunch of even numbers. You have, how many odd vertices? You have 0 odd vertices, which means this graph is traversable, and it's also an Euler circuit. And so what do we have here? This one, number 8, lives right in the middle of that Venn diagram. You don't have to do this Venn diagram when you're doing your homework. You just have to answer yes, yes. Okay, now before we finish up this lecture, I'm going to tell you something that's a bit scary on these. Let's go back to this one right here. We have 2 odd vertices, that one and that one right there. Well, isn't it true that I could have put another vertex right there? I know what you're thinking. You're thinking that's cheating. So some of you may want to skip over this because it's going to be a little high level. And that vertex there would then be labeled 2. And isn't it true that I could have put another vertex like right there? And that vertex would be labeled 2. And I could put another vertex right here. Now I wouldn't do this when you were doing your homework. And that one could be labeled 2. So some graph theorists consider graphs to have infinitely many vertices that are labeled 2. Because there's infinitely many points just within this line segment, and each of those points, if I want to convert that to a vertex, it gets labeled 2. Pretty scary thing. So you don't have to consider that, but I thought that was kind of cool. So let's get back to our puzzle. What do these letters have in common? So we're finished with 5.1. We have some letters here. So why couldn't we put B in there or C? Now if we were allowing numbers, we'd be able to put 4 in there, but we couldn't put 8. So the deal with this puzzle is these letters have in common, what they have in common is they're made up of straight lines. I really should say straight line segments, but I'm lazy, so straight lines. So straight lines make up all those letters, and any other capital letter that I can think of, even the letter D, they have curves to them. So this completes 5.1. Our next section is 5.2. You guys have a good day. We'll see you in the next video.